There we go. So happy Thursday. Happy Thursday. Yeah, not happy garbage day. Happy Thursday. Which means almost to another weekend. I should have gotten an email from me yesterday that you have a formative assessment available. So that is due Monday night. As usual, it is 2 points for making an honest attempt. Try to do it from the top of your head if you can, but consulting your notes is totally fine. And if you have questions that you want to go over that are related to those questions or otherwise, please put them in the answers so that I can take a look. And we'll go over it on Tuesday. A few of you are behind in your formative assessments, and so if you're missing some, you can still do them. I just take off a half a point for being late, but that will add up to quite a bit if you don't do them. So I would encourage anyone who hasn't gotten them all done to get caught up in that. You don't yet have a homework available. That's on me. So I will let you know as soon as it is available. I hope to have it done no later than the end of the weekend, so that you have at least a week to work on it. Let's see. Anything that you want to talk about or review? Questions to start with? No? Okay. Well then, let's see here. I got this as a prompt. Yeah, hit me.
I was having a hard time figuring out. I saved my data output from SAS, but couldn't figure out how to access it later because none of the programs seemed to have wanted it. Somebody had told me to put something at the bottom. Oh, just the ODS RTF close, and then we can open it from SAS or from Word, or what does that allow us to do?
Okay, so are you referring to the output or the data set that you saved?
The output.
The output, yes. So let me open something so that I can show you what that looks like. One second. All right, so here's an example. I'm going to make it any bigger. View in web browser. Yes, if I do that, then it will be bigger, assuming it works. So when I build my examples, I have this piece of code right here. Oh, it opened it in SAS. Okay, well, that's not helpful. One second. There we go. So this piece of code right here, ODS RTF, what that does is open a rich text file, and then any output that you subsequently ask it to do will go to that text file. And when you're done with everything that you want to have in it to save, then you would execute this little line of code here, OTS RTF close. And what that does is close the file. And depending on whether you're in the virtual desktop or not, it sometimes opens up right after that. But if it doesn't, it should be in the same place where your data set is that you referred to with this file save location at the top. And that is actually how I make the RTF files for your examples. So the one that goes with that, let me open it here, this is what it would look like. So it has all of the output that would be directed to that place. Okay. So I have that sort of as a sandwich. Open it and then put the stuff in it and then run that, and you should have this output then to refer to.
Okay, thank you.
Yeah, and then I have that in actually all three packages, because in the download packet I have the output saved for all three. That way you can refer to it without having to run it. So in Stata it's called a log file, and it just prints a text file, and then I found an analog to do that in R as well. So you should be able to save your output without actually having to paste it into some other document. So, other questions? No? Okay, then tell me what you remember from Tuesday. And here's a prompt to help you remember what Tuesday was about. As usual, I would take words, gestures, symbols. What were we talking about on Tuesday?
Besides the Pearson family?
The Pearson family, yes we were. No, that counts, because that was what we covered on Tuesday. So I introduced you to the cast of This Is Us as a basis for an analogy. The Pearsons, just to describe unique predictors. So yeah, the Pearsons, this was my story. The idea of the family pitching in to clean their house, and two things to consider. How many rooms did each person clean that no one else cleaned, so that they each get a Nintendo per room? And then how many rooms in the house got cleaned in total? Because then that's ultimately the objective, right, is to get a cleaner house. Who does what is less of an issue if you're not trying to assign individual credit. So yeah, so how does this relate to this class? Multiple predictors, yeah. So the house is your outcome variable. The people cleaning the house are your multiple predictors. So once we start putting in more than one predictor into the model at a time, we pay attention to two different things. Sort of how much of the house got cleaned is how much of the total variability in Y did we predict. And there's a statistic for that. If I asked you a question on homework, for instance, how much of the variability in Y did this model capture, what would you be looking for? What do you think?
Is it F?
F is the test of whether that's significant.
Okay.
Yep, you're in the right neighborhood.
Okay.
Yep. What goes with F then, in terms of how much of the total? Like how much of the variability was explained by the model? What proportion of the house got cleaned?
Is that R squared?
Yeah, R squared. And yeah, the inverse or the opposite of that rather would be like E. So E is the idea of a per person residual, and we want to keep track of the variability across people in those residuals. So what's not E is what's explained. So yeah, R squared is the proportion of the house that got cleaned, so to speak. So in my story here, 9 out of 10 rooms, so this would be like the Pearsons accounted for 90% of the mess, and they did not get the garage cleaned. But then the other piece of that is the idea of what did each cleaner contribute independently, what did each predictor contribute independently to getting that R square. So that's the new pieces, the idea of competition amongst the predictors, unique effects. Yes, indeed. So two pieces then. I like the Venn diagram for this. So trying to describe this with this type of diagram instead, in order to make it work for the Pearsons, I'd have to add more circles. But so pretend like this is just two people. So Y is the house. That's the outcome we're trying to predict. X1 got this much of it, this overlapping area. X2 got this much of it. But if we break it down as to what each got uniquely, X1 got area A, X2 got area B, they both got overlapping area C, and nobody got E. So when it comes to building an R square for the model, common and unique count in the numerator there. And the total is everything, so all the parts of Y. So it is literally total in the denominator in this case. When it comes to interpreting each predictor's effect, though, the way that we talk about the slope is what each predictor captures uniquely that no one else did. So even though C is part of the R square here, this amount of prediction is not going to be given credit to X1 or X2. So it is technically possible that you can have a significant model that captures a lot of the variance with no individually significant predictors. That can happen, because if they overlap a lot, then none of them gets credit for enough uniquely. But together, what they have in common still contributes to the R square. So we talked about that. Let's see. Standard errors then also change, and the new piece of the standard error formula shows up right there, unique variance in X. So all things being equal, if you have an X that is more related to the other predictors, it has less unique variance to it. its standard error for its slope is going to be higher. It gets harder to figure out what the unique contribution is of each predictor the more overlap they have. And that basic type of problem is called collinearity or multi-collinearity, and there's not much you can do about it other than changing what goes into your model. All right, so I think we left off here the idea of how do we quantify effect size for each predictor. So let me back up a second. Why do we need effect size?
So we know how much is affected by each slope?
Yeah, so we need, So we want to know sort of in a more general metric the size of the relationship that each slope is contributing to the model. Because the slope is always going to be in units. So it's in dollars or pounds or years or whatever X is. And so just looking at that number isn't going to tell us really how strong the effect is. Likewise, if we wanted to compare slopes and say, what's the most important predictor in my model? I can't just look at their numbers and answer that question because they're all on different scales. So it would be like if I wanted to say, who weighs more? This person who weighs 150 pounds or this person who weighs 70 kilograms? Like, I can't do that math in my head. I think they're about the same, but I'd have to check. But you can't just look at the numbers and tell if they're on different scales. So effect size is used to convey the absolute magnitude of an effect without the units, so taking off the units. But then it's also going to be used to judge which predictor is relatively most important. So two pieces for that. Why can't we just look at the significance test? What else does significance take into account besides effect size? Power. And power is a function of effect size and alpha, which is usually fixed in one other really important thing. Sample size, yeah. More people, more power. More people, more power, because you have a smaller standard error. So the more people you have at the same level of effect size, the more likely that effect size is to be significant. So you can have a slope that's significant at p less than 0.0001, not because it's big, but because you have enough people. And so that's why we always want to qualify the results of a significance test with an effect size simultaneously. All right. Any questions or other things that you want to review before we jump back in here?
Can you repeat the two kinds of purpose of the effect size?
Say that one more time.
Can you repeat the two purposes of effect size?
Two purposes of effect size. One is to convey the absolute size of an effect in units that are readily interpretable. So you don't have to know how you've measured the variable. Like if I tell you it's R of 0.3, you know what to do with that information. You don't need to know if it's years or pounds or dollars or whatever the scales are. The other, and this is relevant when you start combining predictors into the same model, is to see which is the most important. So is this outcome more related to X1 than it is X2? You have to put them onto the same scale, so to speak, to answer that question. Yep. And the other piece of it we talked about at the end of class last time, so let me put the slide back in here. Future people will thank you. So people who are doing meta-analyses and who want to include your study, you want to be able to give them enough information to either use your effect sizes or to be able to compute additional effect sizes out of your data. And other people who are going to be using your study potentially might want to plan their own study using what you found, and you can help them to predict how many people they need to have adequate power. So effect sizes are useful for conveying lots of things, not just within this context, but helping to contribute to a broader literature more generally. So then the question is, how do we do it? And this is admittedly something that I was like, whatever before. I didn't pay as much attention to it as I should, and then I started getting my head into it, and I'm like, oh, this is actually more complicated than I thought. So I want to try and make it less complicated, but also try to make it comprehensive with respect to what are your choices and what do they mean. Because there's not necessarily one rightest way to do things. It's always context dependent. So what I want to give you are choices. I'll give you my opinions. You get those whether you pay for them or not, right? Those come free with the presentation here. But the most important take-home message is, regardless of whatever you choose, explain exactly what it is. So I've read people's grant proposals where they say something like, I have adequate sample size to detect an effect size of 0.3. And my response to that is, I have questions. What is that? Is that an R? Is that an R square? Is that a D? Is that a G? Is that a delta? Like, what is the metric of my effect size? Because you have to know that to interpret what 0.3 means. But then also, power for what? Is that the power to detect a significant R square for the model? Is that the power for one slope? Is that the power for one predictor, which is composed of multiple slopes? Like, what is that? So the most important thing you can do is be clear about what you have done. And so I want to try to give you enough language and enough documentation so that when the time comes, you'll be able to describe exactly what you've done. And then reviewer two can argue with you as to whether you should have done that, but at least they'll know what you did. So there's choices in an R metric, a D metric, and an R squared metric. And this is where we hit into things that are functionally labeled differently but are secretly synonyms. So things that are called eta, this Greek letter right here that looks more like an N than an R, that is in an R family. So those are in a correlation metric where it's -1 to 1 is the range, and 0 means no relationship. There's also omega, which is also in an R metric, but is the version of the effect size that corresponds to adjusted R square. So R square is based on sums of squares for the model divided by total. Adjusted R square takes that and downplays it for low sample sizes, essentially. So if you are going to be reporting adjusted R squares, you want the omega version of these things. If you're reporting regular R square, you want the eta version. And so this is what it's called, like on your outputs. Like in SAS, it's called eta and omega. In Stata, it's called R and R squared. And in R, it depends on what kind of package you have and who wrote it, what it's called. So here's how these things differ from each other. So first, standardized slopes, because this is still probably the most common thing that you will see, and I want you to know why they are not actually as useful as you might think. So we did this to start with. In homework 2, for instance, I asked you to compute a standardized slope, and if you only have one predictor in the model, the standardized slope for that predictor is the same thing as the Pearson correlation between that one predictor and the outcome. So a standardized slope is if you converted every single variable in your model to a z-score metric. So if you converted it to a metric where you have a mean of 0 and a standard deviation of 1, and then you ran your model, the results of the model would be standardized. So your intercept will always be 0, because the purpose of an intercept is to adjust for mean differences between the scale of your variables. And the slopes themselves, if you only have one, would be the same thing as a Pearson correlation, and it ranges from -1 to 1. So what I hadn't realized, to be honest with you, until I started reading more about this, and I think your textbook, by the way, does a really good job of explaining this in Chapter 8, and here's also a blog post that I found that I thought did a good job of explaining it. This idea of standardized, meaning that it's a standard deviation and X corresponds to this much change in Y, breaks down once you have more than one predictor. Because the original predictor standard deviation of 1 is not the same as its unique standard deviation of what it has that the other predictors don't have. It's not on the same scale anymore. So even though all packages readily provide standardized slopes, And people like to think about them as it's the change in y for a 1 unit or a standard deviation change in x. That's not technically correct. So standardized slopes, once you have more than one predictor in the model, do not range from -1 to 1. They range from plus or minus infinity. Because it's a standard deviation of the predictor is not 1. It's whatever it has that the other predictors don't have, which depends on the particular combination that you have for the problem. So it turns out that if you try to fix this, if you take your standardized coefficient and you're thinking that it's supposed to be on a scale where every standard deviation is 1, and you multiply it by what the standard deviation actually is for your predictor, the part of it that uniquely is eligible to contribute to y because it doesn't overlap with other things. So the idea of unique variance is the square root of something called tolerance. That works out to another effect size that I'm going to talk about next, which is semi-partial r. So people want to talk about these as this is the change in y per standard deviation of x, but that's not right. It's because they're talking about original x's standard deviation, not the part of x that's eligible to contribute to y that none of the other x's have. So let me go back to the picture here, because I think graphics help with this. Here, there we go. Not that picture. The Pearsons are coming back in a few slides, but not right now. So like if we look at the pink circle here, I can take that variable and I can feed it into my software and get a z-score out of it. All software packages have this option, or you can do it yourself. So you would take the variable, subtract off the variable's mean, and divide by the variable's standard deviation, and that makes a new version of the variable where the mean is 0 and the standard deviation is 1. The standard deviation of 1 describes the whole pink circle. But the only part of the pink circle that's eligible to relate to y is the part that's not covered by green here. I'd have to like take this, like a Pac-Man, like chomp that part out, and then what's left, and figure out what the standard deviation is of what's left. And that is what goes into the model. So that's not the same. So that's one issue. The other is what happens when you get interaction terms. I'm finding it. This is the part where I hate animation. There we go. Back to the slide. So what happens if you, say, want to fit a quadratic effect? So there's two ways to do that with respect to trying to get a standardized slope. One way is to standardize my predictor, so make it so that it has a standard deviation of 1, multiply it by itself, and then put that into the model. The multiplied result is not going to have a standard deviation of 1 anymore. The other way to do it is to take the variable and multiply it by itself to create the squared variable and standardize that instead. And those are not going to be the same thing. And it's unclear which of those is more correct. Do you standardize before or after the multiplication? You get different answers. So the same thing is true when you have interaction terms, which is what we're talking about in the next unit on moderation. Another potential problem is that the idea of a standard deviation change makes 0 sense if you're talking about a categorical predictor. If you have, say, group A versus group B, a 1-unit change means you're moving from group B out of group A. There is no standard deviation. Like that doesn't mean anything. And if you have the same mean difference between group A and group B, that will get translated to a different standardized slope if the groups have equal sample size than if they have unequal sample size. Because unequal sample size changes the variance of the variable, which changes the standard deviation, which changes what the z-scored version of it would be. So you can end up with a smaller effect because you have an unequal distribution across the two groups relative to the same variable with the same mean difference that has an equal distribution. So that's problematic as well. And then finally, you can't do this in any of my other classes. So once you lose this idea of there being only one kind of residual variance in the model, you can't make standardized effects. So there's no such thing as a standardized slope in generalized linear models, which would be the next class I would recommend after this one. That class addresses these sorts of regression prediction models for any other outcome besides something that's supposed to be continuous. So if you want to predict a binary outcome, a count outcome, proportion correct, things that are not going to be normally distributed with their residuals, there's no such thing as standardized slopes in those models. And there's also no such thing as standardized slopes in multi-level models, which is where you have more than one type of residual variance that corresponds to more than one type of sampling. So for reasons, standardized slopes are not as useful as they're made out to be. Okay, questions on that? Have I convinced you? I feel like I'm like a used car salesman, like, come on. Except I'd be convincing you to buy them rather than not buy them. I'm a very bad salesman, as it turns out. So, except when it came to Girl Scout cookies.
Yeah. Too easy sell.
Yeah, once upon a time, I walked up and down my street selling Girl Scout cookies, like manually. You know, I didn't have like an Amazon website or something like they have now. And I remember my mom, I had a Girl Scout uniform from the thrift store, like secondhand, and it was like this sort of sad, like faded, you know, green, and all the other people in my troop had a bright green version, right? And they had a vest. I only had a sash, and they all had vests. And I was like, can you buy me a new Girl Scout uniform? And my mom was like, okay, if you sell 100 boxes of cookies this afternoon, I'll buy you a new uniform. 4 hours later, boom, come home with my sheet. Mom. And she's like, seriously? You sold 100 boxes of cookies? So I can do it. I almost wanted to major in marketing, but then ultimately changed my mind. And
We're
so
glad you did it.
I know. Now I sell models to people instead of cookies.
You do a great job.
Oh, thank you. This is much more fun, but I did get the vest.
There you
And
go.
what's sad is that I have like a pile of badges, like in my, like we all have like storage boxes that we sort of cart around with us of all the places we live, the things that we can't bear to part with. I have like a pile of badges that never got sewn on the vest. I keep them though, because like at one point in time they meant a lot to me. But yeah, I sold 100 boxes of cookies in one afternoon. I can sell you effect sizes too. I can do it. I'm selling SAS, I'm selling Stata, I'm selling R, selling quantitative methods. Yeah. The other thing I wanted to be was a psychologist who helped people. And turns out I am a psychologist who helps people. I help them with their data. And don't think that people haven't cried in my office before over data.
I bet they do.
They do cry in my office. You know, back when I used to actually see people in my office, you know, back then. But I have Kleenex on my office just for the crying that happens with the data. But anywho, no Girl Scout cookies today. But for the record, it is, I think they're Caramel Delights is what I know them as. Mm-hmm. They're called something else depending on where you live in the country. Samoas, yeah. And the mint chocolate things are the worst abomination in the history of the world. Mint and chocolate together is just wrong, and I will stand by that opinion.
The only thing I've ever disagreed with you on, Lisa.
I know. It's very polarizing, but literally the smell of the mint chocolate, the Thin Mints, or like the York peppermint patties, like that smell just makes me want to hurl. It's just that combination. It's like, no.
That's funny because there's a meme going around of like people dumping cookies in like vapor rub because that's like the equivalent to mint chocolate chip.
Oh, mint chocolate Vapo Rub. Yeah. That would be like Ipitac. Isn't that the stuff you give children to make them puke? That's what that would be. But yeah, no, it's just a no for me. But anyway, TV, cookies, sleeping. Yeah, anywho. I'll sell you anything. That's my point. Now I'm going to sell you some effect sizes. What's it going to take to put you in a new semi-partial? So to start with, what some people call semi-partial is what other people call part. So that's a synonym that you will come across. So given this type of model here, and given, so it's the circles haven't changed. R square is still what x1 brings to the table uniquely, what x2 brings to the table uniquely, and then c for their common. Here's what semi-partial eta square would be. So this is in a squared metric, which means it's going to give me some kind of proportion of variance. And the way that you compute semi-partial eta squared, say for this predictor x1, is the amount that it does that no one else does over the total. So it would be A over total in this case. So this is the one that I personally like the best because it is the easiest to explain. A predictor's semi-partial eta squared tells you how much of the R squared that predictor did. The end. That's how much it did. So because it's out of total, there is no way to make this effect size look artificially good. So you can add other predictors and that will improve the R square, but the part that A does is always going to be the same. Like it's always over total. You can use the t-test statistic to get this if you want. You can also ask for it directly, and I'll show you how to do that. But it takes the t-test statistic and basically corrects it for the amount of variance that is not explained by the model to put it back in. There is no version of this that goes with D, though. So this was something that I actually had to check with one of my colleagues, Ariel Olowe, whose expertise is in effect sizes and meta-analyses, and he confirmed that no. Because the way that you compute a Cohen's D, if you were to just use the raw data, would be the mean difference between groups divided by the within group standard deviation. So the denominator to D already presupposes that you've explained some of its variance by putting in group. So there's no version of total that you can come back to because you have to know the effective group in order to get it. So there's no analog to D, there's just the R version or the R square version. And given that the R square version directly corresponds to a number that I know what to do with, that's the version I prefer. So that's how much of the R squared this variable is responsible for. That's what semi-partial eta squared tells you. So if you look at this in SAS, it will be called semi-partial eta squared. If you look at it in Stata, it will be called semi-partial R squared. So I'm going to write this out several times just to make the point that these are functionally the same thing with two different labels. Okay, with me so far?
So if we went back to the house
Mm-hmm.
and we said, for simplicity, that 90% of the house was cleaned,
Yep,
and then we could say that Kevin did 10% of it was uniquely Kevin.
yep,
Okay.
exactly. So if 90% of the house is clean, actually that's like 4 slides from now. I'm going to do that for you.
Okay.
But yes, thank you for setting me up for that transition. So if 90% of the house was cleaned and Kevin did like 1 room out of the 9, then Kevin's responsible for 10%. 90 total. It's not 10% of the 90, but it's like the amount. Yep. Yep, exactly. So here's something that sounds very similar, but is very different. So before it was semi-partial, this is just partial. These are not synonyms. They start out the same. The numerator is A. The denominator is A plus E for this variable. So if this were for x2 instead, it would be B over B plus E. So the numerator is still what does this variable bring to the table uniquely, but relative to what? And the denominator is what's left after the other predictors had their say. So this statistic can be artificially inflated by adding other predictors to the model that reduce E. That's both good and bad. This is the version, though, that corresponds to the interpretation of your fixed slopes, because each fixed slope is describing what it does uniquely that none of the other predictors do. And the residual variance of y is what is used in forming its standard error. So this is what we did in your last homework, for instance. I had you compute these, and I also gave you a formula for R, but you haven't used it yet. You can compute these out of the t-test statistic. And so sometimes people talk about slopes in multiple predictor models as partial slopes because of this. It's the idea of what does it do uniquely relative to what's left. So what is it eligible to predict that nothing else has yet predicted? So here's putting the two side by side. The numerator is the same, the denominator is what's different. And then there's one more that you'll come across, which is Cohen's f squared, and I honestly don't know what the hell to do with this. It's a over e, and if it were for the other variable, it'd be b over e. And the only reason I mention this is because programs like GPower and other software programs that do power analysis will refer to this in the context of regression. So I want you to know what it is for that purpose, but I honestly don't know what to do with it in terms of an explanation. So now back to the Pearsons to try and explain how you would talk about these numbers. So let's say that we have a new scenario here with the Pearsons. We're just limiting it to Randall and Kevin, since I've only got room for 2 circles here. So of the 10 rooms, let's say that Randall cleaned 4, Kevin cleaned 1, and then they cleaned 2 that were in common. So according to this diagram, A would be 4 for what Randall brings to the table uniquely. Kevin's B would be 1 for what he does. C would be 2 for their overlap, and then there'd be 3 rooms out of the 10 that didn't get cleaned. So if I were to compute semi-partial and partial eta squares to describe this, let's do Randall first. His SR2 here, that stands for semi-partial r squared or semi-partial eta squared, would be his 4 over the total, which would be 40%. So that would be of the amount of the total house, Randall cleaned 40% of it. His partial eta squared or partial r squared would be his contribution over his contribution plus the remainder. And that's much higher. It's 57. So the interpretation would be that Randall cleaned 57% of the house that Kevin didn't. So it's like setting aside what other people did and just focusing on like how much of the remainder he's responsible for. So the more that you can set aside that other people did, the higher this number is going to get, but the semi-partial eta squared would stay the same because the denominator stays the same. So let's look at Kevin's. Kevin's semi-partial eta squared would be 0.1. So Kevin cleaned 10% of the house. So if we put it together, it looks like Randall cleaned 40% of the house and Kevin cleaned 10% of the house. We can just talk about it that way. But Kevin's partial eta square would be what he did over the remainder, which is 0.25. So Kevin cleaned 25% of the house that Randall didn't.
Which one do you find to be more useful?
The one that I find more useful is semi-partial eta squared. So question, so is the total of partial eta squared for all the predictors more than 100%? Yes. Yes, because they're not out of the total, they're out of the total that's left. So out of the original total, I think is a more fair way to talk about it. Because otherwise it's a sliding scale based on what happens to residual relative to the rest of the model. So if I bring in Kate, right, she's the third member of the big 3 in the family here, and Kate cleans another room. Randall and Kevin's effect sizes with respect to semi-partial eta squared would stay the same. Because the denominator stays the same. It's just that Kate would be lumped in here, the 3 would be spread into what is residual and what is Kate's. But in the partial eta squares, the 3 would be reduced. So then it would be Randall's partial eta square is how much of the house he cleaned that Kate and Kevin didn't. And Kevin's would be the same. So this becomes problematic from the perspective of comparing results across studies. Because if you have, say, the effect of, let's go with, screen time on child outcomes is my favorite example. If I have a study that's looking at screen time and childhood outcomes, I have effect sizes. I have someone else who's looking at that same problem, but now they're controlling for number of siblings and socioeconomic status and whether the parents work full-time and a whole bunch of other things. The same effective screen time with respect to semi-partial eta squared would become very different effects of screen time for partial eta squared. Because that didn't already get predicted part shrinks, and it looks like you have a bigger effect. Okay, how are we doing with this? I'm seeing some frowny faces, or some thinking faces. My thinking face is a frowny face too. That's fine.
I have a question about the overlapping part, like the C part. So when you say the total of X1, like the total of Randall is 57% and Kevin's 25%. I just want to know the C, is it like divided to add to what Randall did and what Kevin did, or
No,
is C the whole thing added to both?
C gets kicked out of partial eta squared. So C does not show up because it's like that's other predictors' jurisdiction, that's not this one. Whereas C stays in the story for the denominator for semi-partial eta squared.
So the C stays in the semi-partial eta square, and what is the C in total?
In this story, C would be 2 rooms that they both cleaned.
So the 2 over there is C.
Yes, in this numeric example, to keep the math simple, yes, I put C as 2.
So for both the people got like the full credit for cleaning the room.
Neither of them individually would get credit for cleaning what's in common.
Yes, but like when you see like in total, then they get like the credit. Okay.
They get credit like it'd be like family credit. So if we add this up, if Randall did 4, Kevin did 1, and they both did 2 together, then that is 7 out of 10 rooms that got cleaned. So like the R squared for the model would be 0.7. Even though they both did it, we can only count the rooms once. We can't count them twice because they're not 2 different rooms. So it'd be like, okay, the model, we cleaned 70% of the house. How much did Randall clean? 40%. How much did Kevin clean? 10%. The end. Whatever's left had to be a function of both of them. It gets, the math gets fuzzy then if you're trying to figure out what their unique contribution is without taking into account all the other things that are happening simultaneously, which is what the partial eta squares do.
Will we see an example of this that's using the analogy of our income analogy that we've been using?
Yes, you will.
Okay.
Yeah, you knew I was going somewhere with that, with real numbers. Yeah, so this is where you have to say which kinds you have, and I don't think it hurts anything to give people both, as long as you clearly label what it is. Because if you're trying to compare findings across studies, semi-partial eta square is going to be more comparable because it's out of the same baseline, regardless of how many other covariates they threw into the model. Whereas it's a sliding scale based on how much is left to be residual relative to how many other things they put in the model to try and get the R square up. So here is an example of the income example. Again, thank you for setting that up for me.
I don't even have my computer open.
I know.
I didn't cheat.
It's like foreshadowing, right? So I'm going to show you how I got these numbers in SAS, data, and R, per usual, but I just want to give you the numbers first. So this is from example 2, where we started. So there's 3 separate models that we looked at in example 2. We did an empty model, which is just this. So the R square is 0, because at this point, all of the variability in income is left to be had. When in life, like when you go to do these things and to do actual data analyses, you would not bother to do an empty model for this type of situation, because the total sums of squares in your output would tell you the same thing. This is more of a pedagogical tool to show you like where the numbers, like what R square means is that it's relative to this as a baseline. If you do take any classes with me on multi-level models, we will absolutely start with an empty model, because the goal of those models then would be to decide how much variance we have of each kind. And there's multiple kinds in those models. But anywho, so then we threw in education. This was our very first model with the predictor. And the first time I did it, I did not center education, so we ended up with the crazy negative intercept. The second time I did center it at 12, so then we ended up with an R-square for just education as a linear slope of 0.148. So it'd be like education as a linear slope in predicting education captured income, captured 15% of the variance in income. And this beta 1, if I converted it to a standardized slope, because I don't have to worry about unique X variance, this is the only X in the model, that beta 1 is telling me the same thing as a Pearson correlation. So if I have a relationship between a quantitative predictor and a quantitative outcome, and that relationship is linear, that is the same thing as Pearson correlation. Likewise, if I have a binary predictor, which we had marital status as married people were the 1 and unmarried people were the 0, there can only be a linear effect of a predictor that has a 0 and a 1. The standardized version of beta 2 would be analogous to the Pearson correlation, and this variable captured only 5% of the total variance. So the sum of these two R-squares is this number right here. That is not going to match what the R-square is for the model once we put them together, to the extent that there is a correlation between education and marital status, which is almost always going to be the case. So if we put them together, which is what I'm going to do in example 4a, the combined R-square is actually a little bit lower, because we have to take off what they have in common. It doesn't get to count twice. It only gets to count once. So it's different than the separate R-square that we might anticipate based on their individual contributions. Now, how do we talk about what each is responsible for? That's the new piece of this with the semi-partial and partial eta squares. So for education, the semi-partial eta square is 0.1396. So that I would say that education is responsible for 14% of the variance, and the model overall captured 19% of the variance. The partial eta square is higher. It has to be, so long as there's other predictors to explain the variability. So the way that I would talk about this is that education accounted for 14.7% of whatever variance marital didn't get. And I know, based on the t-test that goes with the slope for beta 1, that that is a significant contribution. So there's a 1-to-1 correspondence if you're dealing with a predictor whose effect is captured by one slope. If that slope is significant, then by definition, all of these effect sizes are significant too, because these are just different ways of describing the size of the effect in a standardized metric. Okay, with me so far? Now the other one. Semi-partial is 0.04, partial is 0.05. Now this is also a significant predictor, but I can't tell just from looking at beta 1 or beta 2 which of these is a relatively bigger contributor to the model. Because beta 1 would tell me the change in income per year of education, whereas beta 2 would tell me the change in income if you become married versus unmarried. And those are not on the same scale. Not even kilograms and pounds. Those are just like completely different things. But if I convert them into effect sizes, now I can compare them directly. I can say that the semi-partial eta square for marital status is only 0.04, so marital status explained 4.23% of the variance in income. But the partial version is that it explains slightly more of what was unexplained by education. And in these two cases, I can easily get either of these two numbers out of any of my software packages by asking for semi-partial and partial correlations, and they will either give me a correlation, the correlation squared, or both. Now I can talk about these. Yes, it looks like education is a bigger deal as a predictor, is more useful as a predictor because it captures more of the variability than marital status. I don't have a significance test for the difference. That would require a little bit more. You can do that, but it would have to be in a standardized metric like this. But I can talk about these numbers as comparing the same thing. It's apples and apples. I can't talk about these two numbers as apples to apples, though, because they're at different totals. Education got 14.7% of what marital didn't get. Of what education didn't get and of what marital didn't get, those are not the same thing. So I like semi-partial because I know what to do with that. That's how much of the R-square that variable did. I feel like that's a very directly intuitive number. Okay. Other questions? Yeah. Next is more complex.
In this situation, the semi-partial is pretty similar to the R-squared. Will it always be that way?
Nope.
Okay.
It depends entirely on the combination of variables that you have. So if you have predictors that have a lot of overlap, the semi-partial will be small because what it uniquely brings that the others don't is what the semi-partial is capturing. If you had two predictors that were completely uncorrelated, then the two semi-partial R-squares for each of them when added together would be the model R-square. Then they have no overlap. It's easy to divvy up what each is responsible for. Okay. Would seeing this much in SAS, Stata, and R be useful? Before we move on to a more complex case? Yeah? Want to do that next? Yeah? Other questions before we change gears slightly and see where I got these numbers from? Okay. Well, then let me show you. So this is the same data we've beaten to death, and I promise this is the last example with it. I'm switching to a new example after this one. Hopefully that will correspond with the beginning of spring, beginning of a new data set. But for now, since we're familiar with the variables. So same setup. In this example, the subsequent model that I'm going to have in here has all of the models that we looked at that were significant in example 3. So in the beginning steps to prepare the data file for analysis, I have done what I normally do in my life when I'm doing analyses and not what I've done in this class up to this point. So in showing you syntax up to this point, the way that I've structured it deliberately is like make the variable, put it in the model, then do another data step where you make other variables and you put those in the model. In practice, that way of organizing your syntax file is really inefficient because you have to like stop and read through it and run this part and then skip the model because you don't need that right now, but then run this part and then skip the model and you don't need that right now and run this part. So having multiple places across the file where you're doing things to your data set when you're going to need all of the things done is going to be much more efficient and easier to work through if you just stick it all together. So that's what I've done. I have, for instance, to start with SAS, one giant set of commands here. See if I can get it all on one screen. Almost. Almost. There we go. So data and set to start with, run to finish it. This is all one thing. And if you want to go back and stick more things in, you can do that. You just rerun the whole thing. So this is all one command as far as SAS is concerned. It's going to open up example 4a, do all the things to it that I asked right here, and then save it as example 4a again. If you're paranoid about screwing something up, which is fair, right? Especially when you're just getting started with these things, you could do something like this. Example 4a version 2. Because then it's saving it as a new name. Your original version is still under this name. So in SAS, you can have multiple data sets open at the same time. You can sort of have different versions. Now, you do want to be careful not to get into what I call file hell, which is when you have like things that all have the same kind of name. Like, does anyone have like a folder for, like, say, their master's thesis that has titles like final version 2, really final version 7, version I sent to my advisor after final version 7 wasn't final. Like, you get into that and you come back to that system, and the only way you know what the end is like to sort by date, right? Like, because presumably the latest one was the last one. When you get into a syntax file where you start doing things like that, it's very easy to lose track of where the stuff is if each time you save it is a different name. So I tend not to do that unless I'm making substantial changes to a data set. So if I'm dumping people out for something, like let's say that I only want to analyze people in group A for this activity, I might make a group A specific data set. But generally speaking, once I know that whatever I'm going to do works, I will put it back to the version so that it's just one file. The benefit in SAS of working in the work library is that it's temporary. So let's say that you do something completely terrible and you erase some of your data. Has anyone done that yet in homework? I'm sure you have. I do that like once a week. No worries. I erase something. Okay, let's just go back, re-import again. Because my original data file is safe and sound, sitting in Excel, and SAS can't touch it. So I live in the work directory, because then I don't have to keep track of all the different versions of data that I was working with. I can just save the original and the instructions. So everything that's in here is just a combination of what was in previous handouts, but all in one place. So I do that for completeness to go with the example, but I also do that so that maybe you can have this as sort of a, how do I make new variables? And here's a whole bunch of different examples of how I make new variables. So in SAS, to make a new quantitative variable, it's new name, for instance, education equals 12, equals old variable that currently exists, and then minus the centering constant. If I forget that part, for instance, if I do this, what have I done? What will happen if I run that? If I don't make a new name?
Will it change the education?
Yep, it'll overwrite the original column. And that,
Reload. Start again.
yep, oops. Okay, so that's not good. What if I do this? It'll yell at me, because it'll be like, you don't have a variable called this. And it won't yell at you in red. It will yell at you in blue, and it will say education 12 is uninitialized. Uninitialized is the politest way of saying, you don't have that. So yeah. If there's a mistake to be made in coding, I've made it before. So I try to make a point of all the options of ways to mess this up. This is how I would make a new variable out of a categorical variable. So when there's a finite number of possibilities, you can do it this way. In this particular case, because what I'm actually doing is just subtracting 1, I could do that instead, and that would be fine. Here's how we do, this is a system called indicator dummy coding, where one of the groups is designated as the reference by making new predictors all equal to 0, and then each other group gets its own predictor to differentiate that group from the reference. You did that in homework 3 as well. Here is an age variable centered at 18, and then here is the piecewise coding, which you'll get a chance to practice a version of in your next homework. So we'll talk more about this one next time, because that's in the more complex model. And then last but not least, in life, you'll need to worry about missing data. So if you plan to keep your sample the same across all the models, which is a good idea, you'll have to kick anybody out who's missing any of the pieces. In terms of strategy for life, that's not the best choice. Because anytime you kick people out, what happens to your power? Fewer people, less power, harder to find things to be significant. Not to mention bias. So for instance, if I had, let's say, people who didn't answer this question, they didn't want to tell me how old they were, and I subset my analysis to people who told me how old they are, those may not be the same people as the original sample that I'm trying to make some kind of inference to a population. So we would call that informative missing data if there's a reason why somebody didn't answer the question and that reason is related to what you're studying. So in those cases especially, you'll want to do something different. And if you want to know what else to do instead, come back. Come hang out with me some more. Come hang out with all the other classes. We'll talk about missing data. There's nothing you can do that's magic, but there's things that are slightly better than dumping cases. Okay, so most of this should look reasonably familiar. Any questions from the SAS folks? No? All right, Stata folks on the next page. Same deal. So I have this in sections that correspond to each part of the example. Gen is used to make new variables in Stata, but otherwise the idea is the same. New variable equals old minus centering constant. We have a replace and then if to do the conditional logic to make a new variable conditional on values of the old variable. And to do the same indicator dummy coding from your last homework, you did a chance to practice, that was there. Here are the 3 piecewise slopes that you'll get a chance to practice on your next homework. And then the row miss function calculates number of missing values and kicks people out if they have any. And then in R. So those of you learning R, you are braver than me. I got to tell you. I think it is quite a big ask to learn these models at the same time that you're fighting through R, so you have my respect if you're doing this process. Because R is, I think, the hardest language to tackle out of the 3. It's written for programmers and not analysts, which is part of the issue. But hopefully with a series of very carefully constructed finds and replaces, you can work with the examples that I've created. So the big difference when making new variables in R is that you have to tell it which data set they're tied to. I believe there are shortcuts to get around that, but that can lead to ambiguous results because then it's not clear where the variables are going. So the reason that you don't have to do that in Stata is that Stata has only one data set open at a time. So there's no ambiguity as to which one the variables are coming from or going to. In SAS and R, you have more than one data set open, the capacity to have more than one data set open, so you have to be more specific in your coding. So we have name of the data set, $, because if you learn how to use R, someone's going to pay you, the name of the new variable, and then the old variable minus the constant. And then to do recoding, there's this additional feature where you have to embed the conditionality right here for the old variable in making the new ones. Here is the indicator dummy coding for working class that you got a chance to practice in your homework. And making squared variables I had to do for this example, even though you don't always have to. I had to for a couple spots, and I'll point those out. And then here's the piecewise example that you'll get a chance to practice in your homework. And again, the which gets embedded in the end here to keep the conditionality alive, to make sure that you're transposing only the cases that make that, that meet that condition. And then we're ready to actually do the thing that we started with. So I would say in your lives, when you start to analyze data, plan to spend about 60% of your time getting the data ready. I'm not exaggerating. Like when someone hands me a data set and they say, oh, it's all cleaned up and ready to go. I'm like, really? Because I have never, ever in like 30 years that I've been doing this or whatever, had a data set actually be cleaned up and ready to go. I always find problems. So this process of like going through and making new variables and making sure all of their values are reasonable and internally consistent, like you cannot overemphasize the importance of that. Because how would you feel if you got all the way through final version 7 of your master's thesis and then you found one of your variables had some garbage in it? Then you have to go all the way back through the beginning. So making sure the data work and are the way you need them to be is the most important part that you cannot forget. But now we're actually ready to do something with the 5 minutes we have left, of course. So here is a summary. I built an Excel sheet that's in your download packet that's where these tables came from, of what happened when the two predictors for linear education and binary marital status were by themselves. So in example 2, this is where these numbers came from. And in the download folder, I re-estimated those models so you could see them again. So I have divided in here effect sums of squares versus residual sums of squares versus total sums of squares. So total is the sum of these two. Effect is how much the variable is responsible for as a predictor. Residual is how much is left. And so this residual sums of squares, when divided by denominator degrees of freedom, becomes residual variance. But all of these things are computed out of sums of squares for right now. So semi-partial eta square, partial eta square, and the model R square are all the same number in each of these models. Because if I only have linear education, for instance, as a predictor, if it's the only predictor, it is unilaterally responsible for the R square. So the semi-partial R square, the model R square have to be the same because it's the only predictor doing the work. And partial R square is the same because there's no other predictors to control for, the part that it didn't get. There is no part for that. So that's why when we were doing this in the first place, we didn't have to talk about any of it. Now we're at the divvying part. So here's my combined model. And it looks in each of the packages probably what you would guess if you had to do this yourself. You stick both predictors in at the same time. So in SAS, the DV, the outcome variable, comes before the equal sign, just like it does in the equation. In SAS, you don't have to refer to a fixed intercept. The beta 0 gets automatically included. So in writing these two variables, I've asked for this part of my model. In Stata, it's the same. Income is first if it's the outcome variable. Here's my two predictors. And in R, income is my outcome variable. Squiggle is its version of the equal sign for the model. I put the 1 there to remind myself about the fixed intercept, but it is also estimated by default. And then I add my two predictors right here. And in SAS, to get the magical new parts, the semi-partial R square and the partial R square, eta square, whatever you want to call them, it's this word right here, effect size. In the one case in which the SAS programmers were thinking like people, what should we call it if there's an option to get effect sizes? I don't know, how about effect size? Yes, love it. Let's do that. And I'm asking for effect sizes using type 3 sums of squares particularly, which means that when we combine models, there is no hierarchy to how the predictors are organized. That is going to be most appropriate the vast majority of the time. The alternative that you might see is type 1, where the order matters, and the way that the credit is divvied up is whoever got there first. Likewise, in Stata, P-core. This spits out partial and semi-partial correlations and correlations squared in one nice little table. And in R, I found P-core test for partial correlations and SP-core test for semi-partial correlations. And because I'd like them to be the squared versions, I asked it to generate that output where it's the correlation between income and education, controlling for this part, and then square it. So this is going into the results and asking it to take that term and square it and then print the squared result. So then it's in an R squared metric. So I did that for education as the predictor, controlling for marital, and then for marital as the predictor, controlling for education. And otherwise, everything is as you've seen before. Ta-da! So next time, then, we'll get to see what happened. And what happened, you already know, but here's all the numbers. So for instance, in SAS, this is an extra table. where they have semi-partial eta square, semi-partial omega square, partial eta square, and partial omega square. So this table is the basis of me saying, if you're going to have effect sizes, say exactly what you did. Because if you said, I'm using eta squared, I'd be like, great, there's 4 of them. So, all right, we will dive back into that next time. So any questions before we call it a week? No? Okay, fair enough. Well, then office hours will be at 3:30. Let me know if you need anything. Please work on your formative assessment by the time I see you next, and I will see you next week. So thank you for being here, braving the sleet and or your couches. All right, bye, folks.